Welcome back. The objective of this video is to spend more time with the inverse of trigonometric functions. You may want to have your unit circle handy, and we will have a calculator problem at the end of the video. So let's begin. If a function is 1-to-1 or passes the horizontal line test, then its inverse relation is also a function. For sine, cosine, and tangent, remember, we have restricted the domains for which each function to discover these properties. And also remember that if we evaluated f of the inverse of x, we got x, or vice versa. If we evaluated f of x of the inverse of x, we also got x. So when you input the inverse into its own function, you get x as your output, and vice versa. And we can apply these properties to sine and cosine and tangent and their inverse functions. So we know that the sine of the inverse of the sine of x is equal to x for every interval from -1 to 1. And remember, these are output values for sine. So those are restrictions, remember, on the inverse. And then the arcsine of the sine of x, or the inverse of the sine of x, will also equal x, but that's from -pi/2 to pi/2. So those are going to be our only inputs, okay? So those are where we evaluate the arcsine, right, between -pi/2 and pi/2. And then the same for cosine. The cosine of the inverse cosine of x is equal to x for the interval from -1 to 1. So remember, those are our outputs for cosine. And then just like we did for sine, now the interval here is between 0 and pi, because that's where we evaluate cosine. We evaluate cosine between 0 and pi. And as we saw with the tangent, a tangent, we can have an output of all reals. So that's our output for tangent. So we can evaluate x at our outputs for tangent. And just like sine and cosine, okay, now we have to look and see where we evaluate the arctan, or the inverse tangent, and that is where we evaluate tangent. Remember, we graph the tangent between the asymptotes between -pi/2 and pi/2. So let's do some examples. Here in example 8, it says find the exact value, if possible, of the following. So here you'll want your unit circle. We want to find the arcsine of the sine of 2pi/3. So we can go to our unit circle and find what the sine of 2pi/3 is. We'll work from the inside out. And we see the sine of 2pi/3 is the square root of 3/2. So now we can evaluate and go back. So the arcsine, or the inverse sine of the square root of 3/2. So we're looking to see what angle value gives us a square root of 3/2 from our unit circle. And that answer is up here in the first quadrant. And that's pi/3. Sample B, we want to find the cosine of the inverse of the cosine of 3pi/4. Well, remember, since this is the inverse cosine here, the values that we're evaluating, these are really the y's. And the y's for cosine go from -1 to 1. That's where we would evaluate the arc cosine. Has to be between -1 and 1. Well, 3pi/4 is about 9/4. So that's about 2 1/4. Well, that's not between -1 and 1. So this inner part here is impossible. That's not defined. So this question's a little bit sneaky that way. It's a little tricky. We think of this as, oh, we just would go to our unit circle and 3pi/4, but that's not what we do. This this is not the angle measure. This is actually the output. This is the y's. This would be the part on that as an ordered pair on our unit circle. So a little bit of dirty pool way that question was asked. So we can't find the arc sine of 3 pi over 4. So the arc cosine of 3 pi over 4 is not defined. So that one, it would be a no solution. Example C, the arc cosine of the cosine of 7 pi over 6. Now we can find the cosine of 7 pi over 6. That is on our unit circle. Okay, and that cosine is negative square root of 3 over 2. So now we're going to find the arc cosine of negative square root of 3 over 2. And that is 5 pi over 6. So remember, we've got to move into the first and second quadrants on our unit circle. So we can't use that value. So it's going to be somewhere between 0 and pi. So we're going to end up at this location. Turning to the next page on example 9, find the exact value of the cosine of the inverse sine of negative 1/2. We can draw a diagram for this if we want. Remember that sine is y over r, so our y value here is 1 and our r value is 2. If we put that on the coordinate plane, that's going to end up in the fourth quadrant, and you may recognize that the ratio of one of the sides to the hypotenuse is 1 to 2. This is actually a 30, 60, 90 right triangle. Theta happens to be our 30, or pi over 6. So our x value here is the square root of 3. So the cosine of this angle now is x over r. So the cosine of theta equals x over r. So that's going to equal the square root of 3 over 2. We'll do something similar in example 10. The sine of the inverse sine of 5/13. Well, cosine or inverse cosine of 5/13. Cosine is x over r. So this is in the first quadrant. We've got an x value of 5. We've got an r value of 13. This is a 5, 12, 13 right triangle. So our opposite is 12. And now the sine, we're going to find the sine of theta, which is y over r, or 12 over 13. And you SOHCAHTOA guys might like opposite over hypotenuse. Example 11, if x is between 0 and 1, and we can include 1, write the sine of the inverse cosine of x as an algebraic expression in x. So I've taken the liberty to label this triangle, and the leap of faith here is that our hypotenuse is 1. So that meets our restrictions. And what I would do is the adjacent side of our theta, I'll make that x, and the opposite is y. So we're going to rewrite this in terms of y. So x squared plus y squared equals r squared, or 1 squared. So y squared will equal 1 minus x squared, and our y side will be the square root of 1 minus x. So now we're going to rewrite this y side as the square root of 1 minus x. So then our sine of theta is equal to the opposite over the hypotenuse, or y over r. So the sine of theta is equal to the square root of 1 minus x all over 1 minus x squared. I have to correct my mistake here. So this is 1 minus x squared, 1 minus x squared. So 1 minus x squared all over 1, or the square root of 1 minus x squared. And in example 12, we'll need our calculator for that. It's an application problem. An airplane flies at an altitude of 5 miles toward a point directly over your house. So the altitude is the vertical distance with our right angle is 5. We've got our theta and our x. Write theta as a function of x. So we want to find the angle, so we're going to use the inverse function. We have an opposite and we have an adjacent. So Chief Sokotoa tells us to use tangent or y over x. So theta will equal the arctangent or the inverse tangent of 5 over x. And now we can, when we want to find theta when x is at 8 miles, so theta equals the inverse tangent of 5 over 8. So we'll use our calculator. We'll do this in both radian and degree mode and get our answers. So my calculator is in degree mode. I'm going to do the arctangent, which is the blue key above tangent. So we'll do second tangent of 5 divided by 8. And that's going to be answering our degrees, 32.005 degrees. This is AP, so we'll go to the nearest thousandth. And if we want to find that in radians, I'm just going to change the mode of my calculator to radian mode and repeat the process. I'll do the arctan of 5 divided by 8 in radian mode, and I get 0.559 radians, rounding to the nearest thousandth for AP. So we'll put our answers in: 32.005 degrees, 0.559 radians, and that wraps up this video on application of the inverse of our trig functions. And you'll get some more practice with this when I see you in class.